So, good afternoon, everyone. Today I'm going to defend my dissertation with the title of Contract Theory Framework for Wireless Networking. And here is the outline of today's presentation. So first I will do an introduction about the motivation of our work and the contract theory itself, and talk about the contributions. Then I will do a quick review of two finished work that we have already presented in the proposal. And then I will introduce two current works that we have already done. Then we will go into talk about the future work and draw the conclusion. So first, let's start with the introduction part. So the motivation of our work is that first, we see there is an imminent wireless traffic boost in current wireless networks, as we see there is an exponentially growing data traffic due to the popularity of the social websites such as Facebook, YouTube, and also the widely adoption of smartphones and tablets. So users now, they have or they will have anywhere, anytime wireless communication. However, as we see, due to the exponentially growing traffic, there is a wireless network capacity crunch. So even though additional spectrum is a tool that can help relieve the congestion of the wireless networks, but we see there is a spectrum crisis. As time going, we have already seen the spectrum deficit. So as we all know, the current center capacity is constrained by the Shannon theory, upper bounded by the Shannon theory. And the possible solutions to solve this capacity crunch is to introduce more access points by making the wireless network more heterogeneous. And technologies such as device-to-device communication, cognitive radio network, software-defined network, small cell wireless network virtualization has been introduced to solve this problem. But to perfectly using those technologies to increase our network capacity, we need the cooperation of those third parties. And the second observation that we have is that we see there is a dramatic growing market of location-based service, such as in navigation, local search, mobile advertisements, emergency notification. And we also see there is a real changing of users due to the various embedded sensors in smartphones. So users now, they are not only data receivers, but also active data providers. However, the sophisticated location-based service is constrained by the adequate and comprehensive location-based data. So the possible solution for this location-based data crunch is to do crowdsourcing, which means there is a large group of users. They regularly transmit data obtained by their embedded sensors on their smartphone to the principal. And we have popular apps such as the Google map, which can provide us the dynamic traffic map, which is one application that using velocity data connected from the mobile users. And we also have other apps such as Yep, which every user, they will upload their preferences, their comments to their favorite bars, restaurant. And also we have the sports tracker who can track everyone's route when they're running or something. And also because in crowdsourcing, we need a large group of users to cooperate. So there is a need of cooperation also in this mobile crowdsourcing. So from the previous two examples, we see that in both the traffic offloading and the data uploading process, third parties, users, they are consuming their batteries, such as consuming their resources, such as battery and computation capacity, and they also meet a threat to their privacy. So motivations are needed to ensure the cooperation of those third party or users so that we can successfully increase the wireless network capacity or to connect adequate location-based data. And so we see there is an urgent need of designing those incentive mechanisms that can consider the third-party users' consumptions during the uploading process, and provide them with necessary rewards, compensations according to their contributions. And the methodology that we adopted is a contract theory, which is usually used to solve the problem of how to regulate monopoly with asymmetric information by introducing cooperation among competitors. And the asymmetric information means that the regulator usually don't know everything about how firms are operating. And the contract situations usually happen between one employer and one or multiple employee, or between buyer and sellers, such as a manager hiring a worker, a farmer hiring a sharecropper. And the scientist who made the greatest contribution to this area is a French scientist called Zhang, who is a Nobel Prize winner in economic science in 2014, and his work is highly evaluated because most economic theory before contract theory consisted of price caps for monopolies and preventing cooperation among competitors, which is the ideal analysis and unpractical in real-world economics. So his work is commented as a Nobel Prize for real-world economics, which is commented by a very famous economic blogger. And due to the property of introducing cooperation, we see there is a great potential to use contract theory to ensure the cooperation in wireless networks. And generally, there are two types of asymmetric information problems in contract theory. The first one is called the hidden information problem, which is usually called adverse selection. And the second one is the hidden action problem, which is usually called the moral hazard. And so what is adverse selection? Let me give an example of a PhD student doing an interview with a professor. So usually when students doing an interview, before they being recruited, the plan they tell the advisor is that I want to be a professor and a major research university after I graduated. But actually, his real plan is that the job market is not very good. So he's trying to look for career alternatives. But the secret plan that he only knows by himself is that he wants to be a baker or rock star or writer, something. So the information asymmetric in adverse selection is that the relevant characteristics of employee are hidden from the employer. So, for example, such as their distaste for certain tasks, their level of competence, and because those preference and their capability or their productivity are their private information of those employees, but available to the employer. So those employees, they will try to respond by pretending to be skilled to get higher wage or get higher probability to be hired. So how can employers respond to this problem, adverse selection problem? So usually they use the revelation principle. That is, they try to offer multiple employment contracts in which there are different contracts designed for different skill level employees. That is, you choose a certain task or a certain performance that you think you can achieve, and then get rewarded by get a certain reward according to your performance. So they will try to select the task that they can fulfill so that they can get a reward. So their type, their capability are automatically reviewed to the employer. So then the second problem, moral hazard. I also give an example of a PhD student. So what my parents think I do in PhD is this: the day I graduate on the ceremony, and what my advisor thinks I do is like kids playing with things. And but what actually I do is that when my advisor presents in the office in the lab, I would at least pretending to work very hard. But when he's on travel, I will do whatever I want. So basically, moral hazard means no one knows actually what I'm doing except myself. So the asymmetric information in moral hazard is that employees' actions are hidden from the employer, such as whether it works or not, how hard it works, and how careful it is. And in contrast to adverse selection, the information asymmetry is arising after the signing of a contract, and also the employee is not asking to choose from a menu of contracts, but from a menu of action reward pairs. So the employers, they typically respond to moral hazard by rewarding their good performance through bonus payments, piece rates, efficiency, wages, stock options, and they may try to punish the bad performance through layoffs. So next, we are going to do a classification of the contract theory. So previously, we discussed the two problems, adverse selection and the moral hazard. And the two problems, they can be classified into, they both have the static contracting and the repeated contracting case. For the static contracting, it's like a one-shot contract, one-shot deal. And for the repeated one is continue. After you first deal with each other and you continue the contract. And for those two problems, they both have a bilateral contracting and a multilateral contracting. So in bilateral contracting, it means there is a single employer or seller try to deal with a single employee or buyer. And in a multilateral trading, it means there are a single employer or seller dealing with multiple employee or multiple buyers. And for the two different for the two bilateral and multilateral trading, they can also be extended to one dimension and multi-dimension. So the one dimension case means the employee only consider one aspect of the employee's capability, or the employer only try to assign one single task to the employee, or the seller only has one item to sell. And for the multi-dimension case, it means the employer will consider multiple aspects of the employee's capabilities, and or the employer try to assign multiple tasks to the employee. And also maybe the buyer has multiple items try to sell as a bundle to the buyer. So for this contract theory models, we try to apply them into three different wireless network scenarios. The first one is the device-to-device communication. The second one is mobile crowdsourcing, and the third one is the cognitive radio network. So here let me talk about the contribution of this dissertation. So in our dissertation, we provide a theoretical research between wireless communication, networking, and economics. And our work has placed a fundamental research on network economics, especially with the framework of contract theory. And also we see our work has the potential to contribute to the future of wireless network economic area, such as incentive mechanism design, pricing scheme design, and resource sharing and trading. So next, let me do a quick review of one of the finished work, the adverse selection in device-to-device communication, which falls into the static contracting and bilateral one-dimension adverse selection. So in our work, we're trying to use D2D communication to offload the cellular traffic. So why traffic can be offloaded by D2D? Because we find that the popular contents are usually requested more than the other contents, such as a famous, very popular video online. So we see the base station is serving different users with the same contents, but using multiple duplicate transmissions, which cause the extra traffic burden for the base station. So if we can transmitting those locally available content in those cell phone to those new requesters, so we can release the traffic burden of the base station. But the main design challenging in this work is that how to incentivize those content holders to participate and share those contents via the D2D communication. So we try to apply the adverse selection because we see there is an information asymmetry in this work, because the base station, they usually prefers users with high preference to participate, and they have high capability, such as they have a lot of popular video on their cell phone. And users, they will attempt to harass more reward by claiming that it is a high preference or high capability user. So because the actual preference capability are naturally known by the user, but unobservable for the base station. So there is an information asymmetry. And we can use the adverse selection model to overcome this information asymmetry by offering different contracts designed for different type of users by specifying a contract bundle with a required performance from the users and a corresponding reward. So the users, they will try to select the contract bundle that fit their own type and review their actual type to the base station. And the second work, we applied the Moore hazard in mobile crowdsourcing, which falls into the static contracting binatural Moore hazard, and we consider both the one-dimension and the multi-dimension model. So in mobile crowdsourcing, how can we incentivize users they continuously uploading data instead of shutting down their location services? So we try to use the Moore hazard model as the service provider, the principal, employs the users to upload data and reward those users based on their performance. So the most simple case is the one-dimension one, in which the principal initialize a crowdsourcing. Then the user try to exert an effort, which is observed by the principal as a performance, which is related to the effort it has exerted. Then it offers a reward package with a fixed salary T and a performance related, kind of like bonus. Then the user will be incentivized by receiving the performance related reward. But sometimes we see there is a necessity to adopt the multi-dimension model, because users, they are usually supposed to work on different tasks. For example, in this figure, we see in smartphones, they have usually it has multiple sensors like this for sensing the remote, distance, and sensing temperature and humidity, and sensing the speed and capture images. So the smartphone itself is working on different tasks. And also the user's cost is not one-dimensional. It usually includes time, power, experience, or anything else. So we see there is a necessity to extend the one-dimension case into multi-dimension one. So in this multi-dimension model, we assume there are n tasks assigned by the employer to the employee. Then for each task, their performance is observed by the principal. Then based on this performance, the principal will assign different reward based on different performance. So this is the extended multi-dimension model. So next, we are going to talk about two current work, and we will go further detail than the previous fast review. So the first work is a multi-user Moore hazard in mobile crowdsourcing. So for multi-user one, we first try to see refer to in the cooperative finance and firm organizations, because usually their output is produced by a group of employees, and the interactions among employees including cooperation and competition. So how can we reward a group of employees? The first method is to evaluate the group's aggregate effort. And the second way is to evaluate their individual effort by their absolute performance or relative performance. And for those three methods, they all have some disadvantages. If you evaluate the group's aggregate effort, so you may meet the problem of free riding. But if you evaluate by their individual effort with the absolute performance, so you may meet a problem called the common shock, which we will discuss in detail in the next slides. And also, by monitoring the absolute performance, the employer will meet a large cost in monitoring their performance. And for the relative performance one, because you only consider their rank instead of their actual performance, so then you lose accuracy. And also the users, they may lose their incentive, because maybe they can do better, but they see, oh, I'm the first place, so I will just do like this. So what is common shock? Common shock is usually seen in economics, such as booming and depression that are unpredictable and typically impact the supply or demand through the whole market. And the common shock can be both negative and positive. So if the principal has a strong incentive to cheat by claiming that the user has a bad performance and deserves lower rewards, so the principal can pay less and increase in their utility, but it is decreased in the user's utilities. And for the positive one is that, for example, in this case, if the wind is blowing in the right direction in this boat racing, so every user's performance will increase and the principal's observation. So if in this situation you try to reward them by their absolute performance, so the users, they can be rewarded more and they can get an increase in their utility, but the principal will lose their money. So in general, the common shock is unobservable to either or both sides, and the incentive mechanism based on the absolute performance can be easily affected. So we try to turn to the relative performance one, which is usually used by designed by the tournament to figure out this common shock problem, because by using the relative performance, the principal has to offer the fixed amount of rewards to users no matter who wins, and also the ordinal ranking is hard to manipulate and easy to monitor. So we try to apply the tournament design into a crowdsourcing, and we propose the network structure with one principal, one service provider, and a fixed group of identical users. And the principal will reward users based on their relative performance, such as their quality of the received data. And we assume there are n users and they are all identical. And we sorted their performance in an ascending order and reward their corresponding prizes for each rank. For example, in this case, the data uploaded by user 1 has the highest performance, so it is ranked as rank 4 and receive the highest prize. And the problem we need to solve is how to design the prize so that every user can be fully incentivized. So the system model is that the principal first initializes a tournament, in which there are n users and each of them exerts an effort. Then the performance is observed by the principal and sorted in an ascending order. Then they offer the fixed price based on their rank, and the user is incentivized by receiving the performance-related reward. So we see the performance observed by the principal is affected by the effort exerted by the user and a common shock that affected everyone equally. So we write the performance equals to this one. This Z is a deterministic item determined by A, and this one epsilon represents the common shock. And Z is a random variable whose distribution depends on A, and which has a CDF and positive everywhere continuous differentiable in AI CDF. And for the common shock, we'll assume it has a distribution function with a mean and variance, and if there is no common shock, this epsilon will be zero mean. And given this Q equals to this, because Zi is a deterministic item, and this is common shock, which is exactly the same for everyone. So if we have Qi larger than or equal to Qj, so we must have Zi larger than or equal to Zj. So the rank order performance depends only on this deterministic item, but not on this common shock. So the realization of the common shock will not affect the game played by the users. So in the tournament, we can analyze the game in terms of just Z instead of this common shock one. So we have the density function for the J's order statistic in the sample of size n drawn from the distribution, which means the user's performance outperforms J minus 1 users and falls behind n minus J users. And this one is the combination of selecting J minus 1 users from n minus 1 users in total. And the probability of user is in the J's place among all the n users is measured by integration of this density function over this Z. So with the probability of achieving a certain rank, so we can define the utility of the user, which is the utility of receiving a price minus a cost in providing the data. And for simplicity, we just write this utility with the denoted by the lowercase w. And for the user's expected utility is the utility for achieving a certain rank multiply the probability of achieving this rank minus the cost in providing crowdsourcing. And because we assume that every user is identical, so we will achieve a symmetric equilibrium. For all users, they will spend the same amount of effort. And for all of them, they will expect an equal probability of reaching any of the n ranks. So in the symmetric equilibrium, we will have the expected utility in this form. And next, we see define the utility function of the principal. So the principal's utility is the summation of all the performance received from the user minus the price it has to pay. And because the performance follows a conditional distribution under a common shock, so the principal's expected utility can be written as integration over the common shock item and integration over the performance. Because the the common shock item can be cancelled out. So the utility can be written by only the integration of the deterministic item z. And z is independent from the common shock, and so here we replace q by z. So here we propose the optimization problem. The objective function is to maximize the principal's utility, subject to the constraint that each user, they will select their action that maximize their utility, which is called the incentive compatible constraint. And the second constraint is that the utility of participating in the crowdsourcing should be larger than or equal to the utility when it does not participate, which is usually called the IR constraint. So from the previous derivations, we can rewrite the objective function in this form. And we can solve the IC constraint by taking the partial derivative regarding the action A, effort A, and also solve the IR constraint by assuming this reservation utility equals to 0. So to set up this problem, we assume that the conditional distribution follows the logistic distribution, which is symmetric and the bell-shaped distribution, similar to the Gaussian distribution, which has a PDF in this form and a CDF in this form. So the partial derivative, which is the first derivative of the incentive compatible constraint, we can get this one. Because if you exert more effort, you will get higher rank. So this partial derivative must be positive. So we can see, in order to keep this one in a positive value, so only j is larger or equal than a certain value, this whole value will be satisfy this constraint. So, and here we define the evaluation function in a power form, and then this one will be a concave function, and the rho will be the power coefficient, which has a value from 0 to 1, and the user's risk-averse degree will be defined in this form. And we see larger because larger value of eta, the more conservative and sensitive the user towards risk, and those two will be negatively correlated with each other. And when also we define the cost function as a convex function with a quadratic form, and C is a cost coefficient. And we do a comparison between the optimal contract, in which there are full information about the common shock, and the principal will reward the users based on their absolute performance. And the second one is a rank order tournament, which is the one that we solved from the previous optimization problem. And the amount of reward is based on the relative rank achieved. And we have larger amounts rewarded to higher ranks. And we also propose the multiple winner case, which is a special case of the rank order tournament, in which there are several top winners share the reward equally. So let's see the simulation results. So first, let's see the structure of the price. And we see that to set up the whole number of users as 19, we see only the users whose ranking is larger than or equal to 14, it will receive a positive value, and which is inconsistent with the previous conclusion that no more than half of the users will be rewarded. And we also see that the higher the rank, the spread, the larger the spread is. This is due to the power function of the evaluation function we have defined. If we define the evaluation function in a log form or linear form, this spread will be different. And next we see the the principal's utility as we increase the number of participants. As we see that as number of users increase, the principal's utility will increase. So that means in crowdsourcing, the more user participates, the better. And we also see that the optimal contract will serve as the upper bound, which is intuitive because it has the full information and it rewards by their absolute performance. And we also see that the multiple winner case outperforms the rank order tournament because this is because the number of participants we have assumed is very small, and if we have large number of participants, the rank order tournament may achieve a higher performance than the multiple winner one. So next, we are going to talk about the second current work, which is the problem that mixed the adverse selection problem and the moral hazard in cognitive radio network. So the motivation of this work is that we see cognitive radio is one of the possible solutions for imminent wireless traffic boost because it can increase the spectrum efficiency by leasing the primary user's licensed spectrum to second users when those spectrums are in vacant. So we see the spectrum, usually the spectrum trading in cognitive radio networks is that the second user can purchase or rent the available licensed spectrum so to satisfy its own need of radio resources to support their traffic demand. And we can achieve the second user's dynamic spectrum accessing and sharing and create more economic benefits for the primary user. And in this case, in this spectrum trading, we try to propose a financing contract. Some existing literature in solving this spectrum trading is the auction theory and game theory. And different from these two cases, we try to give them a finance contract. So we allow the second user to do a financing when purchasing the spectrum as we do for a house or a car. So the second user will pay a down payment as part of the total amount at the point of signing the contract. Then the primary user will release the spectrum to the second user. Then the second user will utilize spectrum to transmit their own package and generate revenue. Then it will pay the install payment from the revenue it has generated. So in this problem, we see there is a problem of adverse selection because the primary user has no idea about how what is the second user's capability in utilizing a spectrum. Just like when someone is trying to apply a loan from the bank, so the bank has to do the background check to see if this guy has the capability to pay the loan. That's the adverse selection case. And also, we have the problem of moral hazard because after the primary user leasing the spectrum to the second user, the primary user does not know how much effort the second user puts into to generate the value, the revenue. So it's also the same when someone apply a loan from the bank. So after it gets a loan, the bank does not know how much effort this guy has worked to get the money back. So that's the moral hazard problem. So the problem we need to solve is how to design those down payment and install payment so that the primary user can get the maximum payoff. And so we propose a contract which has a down payment T and install payment R. And we propose the system model by defining 3 parameters. The first one is the revenue realization. That is, the second user makes use of the spectrum to run its own business, with a revenue realization of a fail, which results in 0, and a success, which results in R. Then, if this business is a fail, so the second user does not have to pay the install payment. And if it is a success, it will pay the install payment. And we assume the type of the capability of the second user may belong to 2 different types, theta L or theta H, so which means it is less or more able at generating revenue. And we also have the operation cost. That is, the second user efforts E. For example, it's transmission power. So the operating cost is defined as a convex function in this form, of convex form, quadratic form, and C is the cost coefficient. And the information asymmetry happens in the adverse selection and moral hazard. For the adverse selection ones, the primary user is unable to observe second user's capability type, but with a prior that second user has a high capability, theta H, with the probability of beta, and with a low capability, theta L, with the probability of 1 minus beta. And for the moral hazard one, the primary user does not know how much effort E it exerts, so we try to combine those problems together by multiplying this capability theta with the effort E. So any increase of the 2 items will result in a higher probability of getting a revenue R. So next we define the payoff, the primary user and the second user. So we assume the contracts offered to different type of second user can be written as TI and RI. So the payoff of the second user is the expected. This is the probability of success. This is the expected payoff. Expected revenue minus the expected install payment, then minus the down payment, then minus the cost in operation. And for the primary user, its expected payoff is the expected its down payment and its expected install payment received from the second user, and which can be rewritten in this form. So the primary user's optimization problem will be written in this form. We maximize the primary user's utility under the incentive compatible constraint that for each second user, they can only maximize their utility by selecting the contract designed for its type. That is, if it is a type I second user, it can only select the type I contract with TI install down payment and RI install payment. If it selects the contract designed for type J second user, like it's a type I, it selects RJ, TJ, then it receives a lower utility. And also it has a individual rationality constraint because we want to ensure that its utility will be larger or equal than the utility when it does not participate. And then we assume that when it does not participate, it will have a 0 utility. So that is the 2 incentive compatible constraints and the IR constraint, so that it can provide the necessary incentive to sign the contract. And we also propose 3 comparisons. So the first one is a contract with both adverse selection and moral hazard that we have proposed in the previous slides. That is, the primary user is unable to see the second user capability and effort, and which is an adequate representation of the basic problem in practice. And we will also propose the optimal contract with moral hazard only, which means the primary user is able to observe the second user's capability. So the quality is guaranteed in this case. And also we propose the optimal contract with adverse selection only. That is, the primary user is able to see the second user's effort, and for simplicity, we just fixed it at a certain level. So the quality may not be guaranteed, but it can drive the incentive of the second user. And let's see the simulation results. And for here, this one is the primary user's payoff and the cost coefficient increase. And this one is the payoff and the probability of meeting a high capable second user increase. So we see in the first figure, the primary user payoff decreased and the cost coefficient increases because when the second user's cost of operation increase, the second user will be less likely to participate. So the primary user must lower its price to attract the second user's participation. Otherwise, the vacant spectrum is wasted and the zero payoff is obtained by the primary user. And for the second case, we see that as the probability of trading with a high capable second user increase, the primary user's probability payoff is also increasing. It is because the second user's successfully probability is theta multiply the effort. So under the same effort, if we have a high capable second user, then it will bring larger expected revenue than lower capable one. So the primary user will try to ask for more payment if it believes it is facing a high capable second user. And also from the two figure, we see that the general problem, the red line, is upper bounded by the moral hazard line and lower bounded by the adverse selection one. It is because in the moral hazard only, the primary user cannot see how much effort it has put into. So it has more incentive to try to work hard and save the cost to itself. But in the adverse selection one, it can only guarantee a certain quality of the product, but cannot drive the incentive of the users. So next, we're going to talk about the future work and draw the conclusion. So the first future work direction we try to do is to explore the more emerging wireless network applications in areas such as network virtualization, physical layer security, multimedia distribution in ultra-dense networks, and load management in wireless network with machine-to-machine communication. And we also try to explore more contract theory models because as we see the previous models, they are all static models. So if we can extend them into repeated contracting, so we can model more sophisticated interplay between different parties. And also, there are many other contract theory models other than those cooperation incentives, such as we can use the insurance design and the audition to apply in the mobile computing, cloud computing. And we can also use the system hierarchy efficiency in the infrastructure deployment design. And the third direction we try to explore is the connection between the wireless physical meanings and economic factors. So because only when we can model and define the economic parameters with appropriate wireless communication network physical meanings, so we can solve the technique problems in wireless networks instead of solving a pure economic problem. And so in this work, we first have to do an overview of the basic concepts, classification as the models of the contract theory. Then we talk about the application of the contract theory problems by applying adverse selection into D2D communication, and the moral hazard model into mobile crowdsourcing, and also a mix of the two in cognitive radio network. And from those applications, we see the potential and the challenges of using contract theory as a tool for designing mechanism in future wireless networks. So this is a publication that I have already got during this 4-year PhD study. And that's all. Thank you. Any questions?